Have you ever wondered how computers sort data? It might seem like magic, but it's actually a culmination of various clever techniques. Today, we are embarking on a journey through the captivating realm of sorting algorithms. They are the unsung heroes of computer science, working behind the scenes in countless applications, from organizing your emails to rendering your favorite web pages, and even in the search engine you used to find this video. These ingenious algorithms allow computers to efficiently sort and organize vast amounts of data in the blink of an eye. They come in many forms, each with their unique strengths and trade-offs, and can be as simple as arranging playing cards or as complex as arranging a library. Understanding them can unlock a deeper appreciation of the digital world around us. So let's dig into the fascinating world of sorting algorithms, shall we? Imagine you have a row of numbers and you need to arrange them in ascending order. How would you do it? You'd probably start by finding the smallest number, right? That's essentially how selection sort works. This sorting technique works by repeatedly selecting the smallest or minimum element from the unsorted part of the array and swapping it with the first unsorted element. This process is repeated until all elements are sorted. So it's like you're consistently selecting the smallest element from the pile, putting it in its right place, and then moving on to the next one. This simplicity, however, comes at a cost. Selection sort has a time complexity of O(n)² in the worst-case scenario, meaning it can be quite slow when dealing with large data sets. So that's selection sort for you. Simple, but not always the most efficient. Now imagine you're popping bubbles. The biggest bubble pops first, then the next biggest, and so on until all bubbles are popped. This is similar to how bubble sort works. Bubble sort is an elementary sorting algorithm that works by repeatedly stepping through the list, comparing each pair of adjacent items and swapping them if they are in the wrong order. The pass through the list is repeated until the list is sorted. The algorithm gets its name from the way smaller elements bubble to the top of the list. Because it only uses comparisons to operate on elements, it's a comparison sort. Although bubble sort is simple and easy to understand, it's not very efficient when it comes to larger lists. Its worst case and average time complexity are both quadratic, making it impractical for most problem sets. Bubble sort, while intuitive, is not the fastest kid on the block. What if we had a more systematic way of sorting? That's where insertion, shell, and Radix sorts come into play. Let's dive into insertion sort first. It's a bit like arranging a deck of cards in your hand. You start with one card, then pick another and place it in its correct position relative to the first. You continue this process, each time inserting the next card in its proper place among those already sorted. Its worst-case time complexity is O(n)², but it tends to perform well with nearly sorted data. Next up, we have shell sort. This is essentially a turbocharged version of insertion sort. Instead of comparing adjacent elements, shell sort compares elements that are far apart, then gradually reduces the gap between elements being compared. This leads to a faster sorting process as it can move elements to their correct position in fewer steps. The time complexity of shell sort depends on the gap sequence used, but it's typically better than O(n)² for most sequences. Finally, let's tackle Radix sort. This clever algorithm sorts elements by their individual digits or letters. For numbers, it starts with the least significant digit or the most significant one, depending on the variant used. It's like sorting a stack of papers by the last digit of the page number, then the second last, and so on until you run out of digits. Radix sort's time complexity is O(n)), where n is the number of elements and k is the maximum number of digits. In summary, insertion sort handles small or nearly sorted data efficiently. Shell sort speeds up the process by comparing elements at a greater distance. And Radix sort takes a different approach by sorting numbers digit by digit or letters in the case of strings. These algorithms provide a bit more sophistication, don't they? Now, let's take it up a notch with merge, quick, and heap sorts. These algorithms use a divide and conquer strategy for sorting. First up, we have merge sort. This algorithm breaks the array into smaller subarrays, sorts each subarray, and then merges them together to form a sorted array. Imagine you're organizing books. You divide them into piles, sort each pile, and then merge the piles together. That's merge sort for you. The beauty of this algorithm is that it performs consistently well, with a time complexity of O(n)log(n) in all scenarios. Next we have quick sort. This algorithm also uses a divide-and-conquer approach, but with a twist. Quicksort selects a pivot element from the array and partitions the array into two subarrays. One subarray contains elements smaller than the pivot, and the other contains elements larger than the pivot. It then sorts the subarrays. A well-chosen pivot can make quicksort highly efficient, with an average time complexity of O log n. However, a poor pivot choice could lead to a worst-case time complexity of O squared. Lastly, we have heap sort. This algorithm takes a different approach. It first transforms the array into a heap, a special type of binary tree. It then repeatedly removes the root of the heap and rebuilds the heap until the array is sorted. Heap sort is particularly useful when you need to find and remove the maximum or minimum element quickly. With a time complexity of O log n in all cases, heap sort is a reliable and efficient sorting algorithm. Each of these algorithms has its strengths and weaknesses, and it's crucial to choose the right one based on your specific needs. Remember, the best algorithm is not always the fastest one, but the one that fits your requirements best. These algorithms are quite efficient, but they also require a solid understanding of the underlying concepts. Last but not least, let's talk about tree sort. This algorithm uses a binary search tree to sort the data. The process begins by building a binary search tree from the elements of the array. Each element is inserted into the tree in such a way that the tree maintains its binary search property. Once the tree is constructed, an in-order traversal is performed to obtain the sorted sequence. The magic of tree sort lies in its time complexity. On average, it clocks in at O log n, making it quite efficient. However, it's important to note that this efficiency is dependent on the balance of the tree. In the worst-case scenario, when the tree is unbalanced, the time complexity can rise to O squared. So while tree sort can be quite efficient, it requires careful handling of the tree structure. The balance of the tree greatly influences the performance of the sort, making it a delicate yet powerful tool in your sorting arsenal. So there you have it, a whirlwind tour of the major sorting algorithms used in computer science. We've explored 9 different techniques, each with its own strengths, weaknesses, and ideal use cases. We began with the selection sort, a simple yet effective method that repeatedly selects the smallest or largest element from an unsorted array. Next, we encountered the bubble sort, which continually swaps adjacent elements until the entire array is sorted. Then we moved on to the insertion sort, a technique that's akin to arranging playing cards in your hands, placing each card gradually in its rightful place. The shell sort, a more efficient extension of the insertion sort, reduces the gap between elements being compared for a more streamlined process. Radix sort, on the other hand, is unique in its approach, sorting elements by their individual digits or letters. This method is particularly useful when dealing with data that can be broken down into smaller, sortable units. Our journey then took us to the realms of the merge, quick, and heap sorts, each employing the divide-and-conquer strategy to different extents. Merge sort divides the array into subarrays, sorts them, and merges them back together. Quick sort partitions the array based on a pivot element, and recursively sorts the subarrays. Heap sort, meanwhile, extracts the maximum or minimum element from a heap until the array is sorted. Finally, we examined the tree sort, which builds a binary search tree from the array elements and sorts them through an in-order traversal of the tree. The choice of sorting algorithm depends on factors such as the size of the data, the distribution of elements, and performance requirements. Each technique has its own time complexity, which can greatly influence its efficiency in different scenarios. Remember, there's no one-size-fits-all sorting algorithm. It's all about picking the right tool for the job. Happy sorting!